Okay, guys, welcome to yet another incredible, glorious, entertaining video about dynamics. Today we're starting on block 13.2, and this is the second of four blocks in chapter 13. We're talking about conservation of energy, and so we have this example problem that we're going to go over. It is asking us to look at the energy at one position versus the energy at another. And I just wanted to take a minute before we get started to explain some things about the conservation of energy. So the last block started with this idea that the differential of work is equal to the differential of F times dr, right? And when we solved this, we got U 1 to 2. And this is the work from position 1 to position 2. Well, this implies that we are going in one direction. And so we integrated and we got from position 1 to position 2. So here we're more interested in making a small change to our math, and there we go. So here, what this means is that this is a path integration, and no matter how far you come back, you arrive back at the same spot. And that kind of makes sense when we think about a spring. So imagine this, this situation, just ignore all of that up there, but let's say that we're not affected by gravity. So we pull this as a starting position, we pull this down, we let it go, and we expect it to oscillate back and forth. More importantly, if we pull this down, then we have some energy in the system, and when it goes and comes back, it'll have the same amount of energy as it did when we pulled it down. So along the path, the change in energy is going to be zero, and we call this a potential energy. And a potential energy is an energy that is dependent on position, right? So you can think of that as in terms of a spring. You can also think of it in terms of gravity, right? So if you have a particle and it goes up and then comes back down, when it gets back to the same level, then it has the same amount of energy, right? In this case, we would expect this to be a decrease in energy, or excuse me, an increase in potential energy as it goes up, but then when it comes back down, it has the same amount. That is the qualifier for potential energy. So when we solve this, instead of getting this equation that has U 1 to 2, essentially what we're doing is we're saying 1 to 2, we're going to split that up, and it means the same thing, but we're going to split it up and be a little more general. We're going to say V1, V2 minus V1, right? So the wherever we are there minus this, and it's, again, same thing, but this is a more general case, and this is work, and this is 2 bits of energy. And we can say that these are energies, right? And so instead of getting, just to finish this, I guess, instead of getting V1, T1 minus T2, like we did before, instead we get V2 minus V1 equals T1 minus T2. And this gives us the relationship V1 plus T1 equals V2 plus T2. And this is the conservation of energy. What this means is that all of the energy at this position equals all of the energy at this position. So the only other thing to know about this is that we can expand these V's. These can expand, and we will in this example. So instead of V1 and V2, what we would say is, let's write it this way, T1 plus V, and it's going to be 1, but we've got two potential energies here, right? We've got a gravity potential energy, and we've got a spring. So I'm going to say VG1 plus VS1 equals T2 plus VG2 plus VS2, right? So it's still the kinetic energy plus the potential energy equals the kinetic energy plus the potential energy at some point further down the path. But we just expanded this, and we could do expansions based on direction. We could, if we have different kinds of energies to consider, but here kinetic and potential energy expand. So let's apply this to our example problem. And let me just rewrite that. So T1 plus VG1 plus VS1 equals T2 plus VG2 plus VS2. Okay, so your governing equation. So in this example, we are given that this is a 20-pound collar. The spring has been extended by 4 inches and has a spring constant of 3 pounds per inch. If it's released from rest, meaning that this is 0, if it's released from rest at position 1, find its velocity at position 2. Okay, well, we can do that. And Jeff gave us a very good idea to split it up in terms of what energies, what the energies are. So let's go with position 1 and position 2. And we'll just tally these things up, see what it gives us. Well, let's see. T at position 1, it's at rest, so this is 0. At position 2, this is a point of what we're trying to find. But we can say, sorry, not this one, this one. So we're looking for velocity. We don't have velocity, but we do have 1/2 m. So let's add that up. So 1/2, and the mass is W over G, right? So 20, and let's see, 1/2 of m equals 20 over 32.2, and that's going to give us 0.31. And the units here are pound times second squared over feet. And so the important thing to note here is that these are feet. That is a meaningful distinction. So this is 0.31 v squared. And the units of the v are feet squared, second squared. So if we times that, feet squared, second squared, then we get pound feet, which is what we should, or foot pounds. Actually, pound feet is better because foot pound, it generally has a connotation of torque. So pound feet, we're going to want everything in terms of those units. And I don't think we need that there. So, all right, so that's our T. What about V, say VG? Well, VG is the weight times Y. So the weight here is 20. And let's do this. Let's say this direction is Y. And then we need to determine what these are. Let's call this one 0, and we'll call this one -6, right? That's our position there. And so at point 0, then the potential energy is 0, right? Because why is it? Okay, and at P2, this is minus 6. So the work is acting downward. So this is positive, this is negative, and that would be minus 20 times 6 is inch pounds. So minus 20 times, actually this is, there we go, minus 6. So that's going to be minus 120, and that is pound inches. So let's convert that to pounds feet. If we divide that by 12, then we get minus 10. Let's see, equals minus 10 pound feet. Okay. Our spring, so that is 1/2 kx squared. So yes equals 1/2 kx squared. And what we have position 1. So it was expanded by 4. So at position 1, we get 1/2 3 8 minus 4 squared, and that's going to give us 24 pound inches, right? And if we divide that by 12, then that gives us 2 pound feet. So 2. Okay, and at position 2, 1/2 3. Well, how far has it gone? Well, this is a 3, 4, 5 triangle, so it's gone 10. And what do we get? We get 10 minus 4 squared. That gives us 54 pound inches. And we want to convert that. Well, let's see. 54 divided by 12 is that 4.5? Yep. So that is 4.5 pound feet. Okay. Sweet. So let's rearrange this. So we get T2 is on one side because we're going to be solving for this. So 0.31 v squared is equal to, so then with the T2, I just switch the sides that I'm recording here. So we would subtract VG2 and VS2 from both sides. And I think, I mean, we could do it in either way. So let's see, VG1 is 0. Let's just do this. We'll say VG1, so 0 minus VG2, which is 10 foot-pounds. So minus 10 plus, and then this is 2, and then it's going to be minus 4.5. Okay, and so what do we get? We get 10 minus 2.5. That is 7.5. And we're going to take the square root. So 3.1. Is that right? Okay, and when we take the square root, then we get that V is equal to, I guess we'd say plus or minus 4 point, and I get 919, and that is feet per second. So assuming that we can this this is plus or minus. Okay, so the velocity at point B, let's assume that it's a negative velocity, meaning it's going down. Well, what's going to happen is it's going to go down, it's going to slow down, and then it's going to come back up. And one of the fascinating things about this kind of a system is that the behavior in either direction is the same. So this is actually true. It's not just one or the other. It would be v equals plus or minus 4.99192, or depending on how you're reporting, maybe just 4.9. At any rate, that is how you do this type of problem, and I will see you in the next video.